Okay, good afternoon, dear participants. So this is Karthik, Department of Physics, VVCE, Mysuru. So dear friends, we know that present trends is in nanomaterials, nanoscience, and their composites and their applications. It is my pleasure to introduce today's speaker, Dr. T. Shivalingaswamy. He completed MSc and PhD in Physics, Bangalore University, and his topic of research is quantum theory. He has published more than 30 papers in national and international journals. He has published 2 books in his name. So he has delivered more than 40 invited talks in various institutions. So he is currently working in as assistant professor in Government College, Mandya, Autonomous. So we are glad to have you, sir. So over to you, sir.
Thank you, Karthik. Hello, everyone. I welcome you all for this 3-day national level faculty development program. Ordaka College of Engineering for giving me this opportunity. Today, I'll be talking on nanoscience and nanotechnologies at an introductory level. As far as the nanoscience or nanotechnologies are concerned, they are not isolated branches. Nanoscience is a horizontal integrating interdisciplinary science that cuts across various sciences and engineering disciplines. So it is not a separate science. It includes chemistry, biology, physics, molecular biology, and various other engineering subjects. At the same time, it is not an isolated technology as well. It, in fact, integrates various technologies like energy technology, chemical technology, telecommunication, computer technology. Disciplinary science, as well as it is an integration of various technologies. We'll look at some of the basic terms that are associated with this nano. Nano is basically a Greek word that refers to a dwarf or for a little old man. Technology is also technology is derived from 2 words. Techno means it's an art or skill, and logy means study. So it is a study of an art that is related to smaller things, and it's an application of knowledge for practical ends. And this science is a Latin word which means knowledge. And materials, nanomaterials, we often use the word nanomaterials. Material is also derived from Latin by the word called materia. That means a substance from which something is made. The actual nano definition was given by European Union in 2011, according to which a or incidental or manufactured material containing particles or as an isolate, where for 50% or more of the particles in the number size distribution, one or more dimensions is in the range of 1 nanometer to 100 nanometer. This is the standard definition that we use now to define nanostructures. You have to understand that 2 things are very important here. One is the size. Size should be between 1 nanometer to 100 nanometer. And in the sample that you prepare, there should be more than 50% of such structures. Then only you can call it as nano. Nanometer is 1 billionth of a meter. It's a very small dimension, and it is a unit of measurement in nano world. Nanotechnology deals with nano-sized particles and devices, and 1 nanometer actually refers to the dimension of 3 to 5 atoms. And the human hair is of the order of micrometer, and 1 by 1000 of the width of human hair will be equal to a nanometer. This is for a comparison of sizes. Atom is about angstrom, that is about 10 power minus 10 meter. And if you consider the sand grains, they will be of the order of 1 millimeter. The nano word is between 1 nanometer to 100 nanometer. This carbon 60 fullerenes, DNA that is present in the biological systems, proteins, viruses, all these they fall under the category of nano dimension. These are some interesting facts. The human fingernail that grows about 1 nanometer every second, and the man's beard grows 5 nanometer every second. That gives an idea of what is nano. Let us start with this science. When did it start? It started with this gentleman, that is Richard Feynman, in 1959 in California Institute of Technology. He just said there is plenty of room at the bottom. Richard Feynman is United States theoretical physicist, and he has won Nobel Prize for quantum electrodynamics, and he is famous for Feynman diagrams. He said the entire Encyclopedia Britannica, 24 volumes, can be recorded on a pinhead. And he said major works on the atomic level, and there is a possibility of direct manipulation of the individual atoms. He said, you can manipulate the atoms, atoms by atoms. You can tailor the materials. This was his idea. So he just expressed in a conference in 1959 at California Institute of Technology, and people took it as a challenge, and they worked on it, and of course they succeeded. And as far as the development is concerned, after this announcement of the theoretical idea, in 1974, this Norio Taniguchi, he coined the word nanotechnology for the first time. And in 1981, IBM developed scanning tunneling microscope. This was a greater milestone in exploiting the characteristics of the nanoparticles or nano devices. In 1985, scientists from Rice University and University of Sussex, they discovered carbon-60 fullerenes. They are also called as buckyballs. They find important applications which we see later. In 1986, Eric Drexler, he wrote a book on nanotechnology. This is actually referred to as the first book on nanotechnology, and the name or the title of that book is Engines of Creation. And in the same year, atomic force microscope was invented by Binnig. This atomic force microscope changed the perception of the nano world. So far, in fact, this technology was there even earlier, but we could able to see these nanostructures with the help of these atomic force microscopes. We'll come to this later. Then again in 1989, IBM made its logo with the help of individual atoms. Just by placing atom by atoms, they were able to create a logo out of the atoms. And in 1991, carbon nanotubes were discovered. And in 1999, Nanomedicine, the first book on nanomedicine, so that was came, that was written by Freitas. This is some important developments in the history of nanoscience or nanotechnology. This gives you a list of Nobel Prizes that have come for nano and nano related research. You can see that the number is big. This shows the importance of nanoscience and nanotechnologies, because you know that Nobel Prize is given only for the area which has some wider implications on the mankind. There are more than 12 Nobel Prizes have come for this nano and nano related research so far. Now the question is whether this is really a new technology or whether this is really a new science. The answer is really not. This was known to our ancestors long back, but not as a science, but as an art. On the left side of this image, if you just look at, they made stained glass with the help of gold nanoparticles. This is there in a church in Paris. This was done around 1250. On the right side, you can see a cup which is named as Licargus cup, and the people believe that it is made in 4th century. But this has a unique feature. You can notice that if you keep the light source inside this cup and if you look at this cup from outside, it appears almost pinkish in color. Whereas if you allow the light from outside, then you will see that it appears greenish. The same material, when light is transmitted through that, it will show one color, whereas if light is reflected from outside, it should show another color. And now we know that this is made out of nanoscience, nanoparticles. That means this technology was there very long back, but this technology was used just by ancient knowledge. That means they used it as an art, but the actual science and the technology came after the invention of the electron microscopes. So we'll discuss about that very soon. And even before this, this was there naturally in nature. You can notice here we have a lotus flower. You might have noticed this lotus flower. If you just put a drop of water on the lotus flower, you will see that it will not make, no, it will just float on that without actually merging into the lotus, because the angle of contact is greater than 147 degree for this. And carefully when you examine this lotus flower, they find that the surface contains nano features. On the right side, you have fancy flower. This also exhibits similar feature, and certain lizards. So if you look at the palms of the lizards, so they can hold the walls very clearly because they have some nano cups or nano fibers attached to them. That means this is just part and parcel of the nature. And what we have done is, we have started mimicking the nature. So in nature, nano is very common. And in the artificial world, we started this as a science or as a technology. This is a summary of this development of nanoscience and nanotechnology. It started in 1959. The science or technology, what we call, that started in 1959, and we manufactured fluorine, discovery of this scanning telenomic microscope. In 1925, the colloids were discovered. They all are in nano dimensions. And as far as the classifications are concerned, nano structures can be classified into mainly 4 groups. This classification is based on the number of dimensions which are not actually confined to nanoscale. That means if the dimensions is above 100 nanometer, then that is actually a classical region or micro region. So that is the one which is used for the classification of this, or for naming of this nanostructures. So we have zero-dimensional materials. That means all the 3 dimensions are confined to nanoscale. One-dimensional materials. That means one dimension is not actually confined to nanoscale, or the other 2 dimensions are confined to nanoscale. Two-dimensional materials. That shows 2 dimensions are not in nano, or in other words, 1 dimension is in nano. And 3-dimensional materials. That means all the 3 dimensions are not confined to nanoscale, but they have certain nano features. And these are some examples for 1D, 2D, and zero-dimensional, 1-dimensional, and 2-dimensional materials. We'll discuss one by one. Zero-dimensional nanomaterials, as I said, these are the materials with which all the dimensions are confined to nanoscale. And generally, nanoparticles and nanocrystals, they come under this class. And these nanoparticles can be amorphous, that means there could be a random arrangement of particles, or there could be uh, erratic arrangement of atoms or molecules. Then they can be called as crystalline nanocrystals. They could be single crystalline, polycrystalline, and they can be composed of a single element or made out of many elements. They can exhibit various shapes and forms. They exist individually or maybe reinforced in a or incorporated in a matrix, and could be metallic, ceramic, polymeric, any kind. So these are various types of nanoparticles that we come across. And as far as the sources of these nanoparticles are concerned, there are 2 important sources. One is natural source, mainly by volcanic eruptions, plants, oceans, dust, smoke, etc. Naturally, from the nature, we get these nanoparticles, and or they could be anthropogenic, man-made. So again, in this man-made group, there are 2 more classifications. That depends on whether these nanoparticles are created intentionally or created as a byproduct of something else. The targeted nanoparticles, that means they are intentionally made. For example, fluorines, quantum dots, nanotubes, graphenes, they are intentionally made. And the nanoparticles that we get from the combustion of the fuels, from the industries, from the constructions, etc., they are just the byproduct of something else. They are unwanted. This is how we classify this based on the source. Nanoparticles are classified based on the source like this. Then, as if you consider the natural nanoparticles, uh, they are very common in nature, and as I said, they are mainly due to volcanic eruption or due to soil erosion, and even the plants and animals, they could be the sources of these nanoparticles. There are various types among these nanoparticles. We have soil nanoparticles like iron, manganese, silicon oxides. So they are of the soil origin. And from water, you can find inorganic minerals, organic colloids, even certain viruses. Uh, they are of water origin. And even in the atmosphere, many mineral aerosols from erosions are found. These are natural, but we focus on the intentional man-made nanoparticles. Now the question is why these are important. So why are they important? Why are we talking so much about this nanostructures? It is because of the size. As I said, that these nanostructures have size from 1 nanometer to 100 nanometer. What is special here? There are certain properties. They do depend on the size. They are called as size dependent properties of the materials. For example, melting point or fluorescence, electrical conductivity, magnetic permeability, chemical reactivity, These things, they do change as a function of size of the particle. For example, if you just look at gold, in the classical scale, the melting point of gold, if you consider it, is about 1064 degrees Celsius. Gold is precious metal, it's a yellow metal, and at the macroscopic scale, it has a constant melting point that is about 1064 degrees Celsius. But when you go towards nano, from the graph you can see that, so if you start from 2 to 10 nanometer, you can see that the melting point varies almost from 500 degrees Celsius to a maximum value. And then later it saturates. Hence, you can see melting point in the nano changes to a greater extent that you can see from this graph. There is a huge variation, 500 degrees Celsius to 1064 degrees Celsius, almost half of this value. So it is 500 degrees Celsius. The melting point changes as a function of size. That is why size is very important. There are various size dependent properties. Hence, to obtain the required property from the material, you can tailor the size and you can harness whatever the property that you want. Okay, that is why these nanostructures are very important. Not only these things, even the colors, say for example, that changes as a function of size. In the beginning of this talk, I told about glass stains. In churches, they used to use this gold to paint the glass. But they are all made out of gold nanoparticles, but are of different size. Why color changes when size changes? It is because of an optical phenomenon that is called as surface plasmon resonance. These nanoparticles, they have high surface area, and if you consider these conduction electrons, and these conduction electrons at the surface, they will be oscillating with certain frequency, and when you allow light of suitable frequency which is matching this oscillating frequency, then there will be resonance, and this is what is called as surface plasmon resonance. And because of that, you will see that the light that is seen by us is complement to light absorbed by these electrons. Hence, different sized nanoparticles will exhibit different colors. You can notice that these are silver nanoparticles, and all these are gold nanoparticles. We just look at the size. So from 100 nanometer to 15 nanometer, if you just change, you will see that the color changes. And again, this also depends on the shape. It also depends on the geometry of the nanoparticles. So color is an important property. Even that also depends on the size of the nanoparticles. That is why these materials are very important for us. And if you consider now the one-dimensional nanomaterials, one dimension is outside the nanoscale. That means the other two dimensions are within the nanoscale. All these nanotubes, nanorods, nanofibers, and nanowires, they come under this category. Once again, very similar to that of the nanoparticles, even these nanowires could be amorphous or crystalline. Once again, they could be single crystalline or polycrystalline. And all those properties which you have studied for nanoparticles can be seen even for nanorods also. And two-dimensional nanomaterials, if you consider, two dimensions are actually not confined to nanoscale, or in other words, one dimension is confined to nanoscale. Nanofilms, nanolayers, nanocoatings, etc., they come under this classification. Again, very similar to the first two categories. They could be amorphous, crystalline, or they could be made of various chemical composition or single composition, and they are generally deposited. Since nano is very small, they are deposited on a substrate, and they can be integrated in matrix material, and they could be metallic, ceramic, or polymeric, etc. As I said before, three-dimensional nanomaterials are not really nano, in the sense, no dimension is confined to nanoscale, or in other words, all the three dimensions will be in the micro region, but they possess certain properties or features which are similar to that of nano. That means, with respect to the presence of features of the nanoscale, 3D nanomaterials can contain dispersions of nanoparticles, bundles of nanowires or nanotubes, as well as the multi-nano layers. They find a very important role in the construction industry, in the civil engineering, because several nano fibers are embedded in matrix to form composite materials, which plays very important role in construction materials. So we'll come to discuss about this later. This is about the classification of nano structures based on the dimensions. This actually summarizes the classification of nanostructures based on the dimensions. You can notice that if you consider zero-dimensional materials, all the three dimensions, Z, X, or Y, say this is X-axis, Y, and Z, all the three dimensions will be in nano, or in other words, no dimensions are outside nano. That is why they are called as zero dimension. Then one-dimensional materials, you can notice here, one dimension is outside nano, that is Z dimension is outside nano, whereas X and Y, they are well within nano. Such materials are called as one-dimensional nanomaterials. We have two-dimensional nanomaterials, that means two dimensions are outside nano. This is not nano and even this is not nano, whereas one dimension is well within nano. And similarly, we will have three-dimensional materials. They are actually not nano, but they have nano features in them. This is about the classification of nano materials based on the structures. Okay, now we'll see what makes this nano special. I told you, the size plays very important role, and because of the size, why these properties should change? It is because of the quantum confinement effects. The overall behavior of bulk materials changes when dimensions are reduced to the nanoscale. And these changes happen because of the confinement of the electrons. This is, in quantum mechanical terms, it is called as quantum confinement effect. For the zero-dimensional nanomaterials, that means where all the three dimensions are in nanoscale, the electrons are confined to a 3D space. Similarly, for one-dimensional nanomaterials, electrons are confined to 2D space. And in case of two-dimensional nanomaterials, the electrons are confined across the thickness, but they are localized in the plane. These confined electrons are like the particles confined in a box. And from quantum mechanics, we know that the energies for these confined electrons are discrete. They are not continuous. If you have a free electrons, energies are continuous. Energy values, eigenenergy values are continuous. Whereas if you have a bound electron, then that bound electron will have discrete energy states. That is what we have learned from quantum mechanics. One can in fact solve Schrodinger equation to apply these eigenenergies. For zero-dimensional materials, where all the three dimensions are in nanoscale, the energy is given by this formula. This is obtained by Schrodinger equation, which you might have done at your BSc level. And this is the energy expression for one-dimensional nano. So one dimension is actually not in nano range. That is why you can see that the z direction is not there. So in z direction, energy values are continuous. They are like free particles. Whereas in x and y, they are bound particles. That is why you have discrete energies here. That means for these confined particles, energy cannot be arbitrary. They have definite values. And if you look at all these expressions, you can notice that this pi h cross is the reduced Planck's constant, h by 2 pi. This is the effective mass of the electron. Nx and y, they are the quantum numbers. And the only variable is L, that is the dimension of the box. And you can notice here, this Em is inversely proportional to L square. That means as you reduce the dimension, you will see that energy increases. That is why a very good conductor at micro scale or at classical scale becomes a semiconductor, or even it can become an insulator when it goes to nano level, because energy increases as length decreases. As dimension decreases, you can see that the energy decreases. That is why gold at nano level is a semiconductor. Similarly, the other materials, silver, say for example, when you take it to nano level, it behaves like semiconductor. Because of this quantum confinement effects, there will be change in the properties of the materials. And now the question is how to prepare these nano materials or nanostructures. Generally, there are two methods. One is top-down approach. That means we start with bulk material and we go towards nano, either by milling or by lithography, etc. And the other method is bottom-up approach. So here we start with nano, and we start with building nanostructure from atom. Just by placing atom by atom, one can develop the nanostructures. This is what is known as bottom-up approach. There are various methods available now. So we have something called a solution combustion method, which is widely used for the preparation of the nanoparticles. Plasma arcing method. Generally, these carbon nanotubes, fullerenes, etc. They are generated or synthesized by this plasma arcing method. We have chemical vapor deposition method, molecular beam epitaxy, sol gel synthesis, an interesting method to develop the nanostructures, molecular self-assembly, then hydrothermal synthesis. There are various methods to synthesize these nanostructures. So these are called as bottom-up approaches. It is very difficult to discuss all of them, so it will be a course. So I'll discuss at least one or two of these. This is a top-down approach. This is called as lithography. Here we either use light or electron beam to selectively remove structures from the precursor. That means you just refer to this graph. So you will be having a photosensitive material which is placed on a substrate. So generally it acts like a film on a substrate, and we allow the light radiation or electron beam through a small hole that is created, and with the help of a mask. So there will be a mask, there will be a small hole which allows this radiation to fall on this photosensitive material. And this that is light interacts with this photosensitive material only in this region. And now if you develop this photosensitive material in a developer solution, it is possible to create a hole, or that means you can remove the other portion, or you can retain that portion. That means here if you use a positive resist developer solution, that will remove the material which is exposed to light radiation or for the electron beam. Or if you use a negative resistor developer solution, then you will see that that will retain this part and it removes the other part which is not exposed to radiation. And you have a nanostructure here. This is how one can develop nanostructures by using lithography technique. And to deposit this nano sample, one can use the atomic force microscope. that is used to deposit the material. And with the help of the femtosecond laser, see this, to create the mass nano structures, the mask plays a very important role. So you should have drills of nano dimension. How to create the drills of nano dimension? That is done with the help of femtosecond laser, which has a narrow beam, and by the help of this femtosecond laser, you can create masks of required geometry, and you can create nanostructures. Now, with the help of this laser beams and this kind of lithography technology, uh, it is possible to uh, develop 3D nano printing. So, three-dimensional nanostructures are made. That is about the top-down approach. There are various other methods like milling. So, just by milling also you can. We have various types of milling. There is, for example, ball milling, etc. There also you can develop nanostructures from bulk material. But those materials are not actually preferred for many reasons, because the nanostructures which are developed by these methods are sometimes, say for example, drilling, if you consider, they are not generally uniform, and they also develop some strain in the material. That is why most of the scientists, they prefer bottom-up approach. There are various methods, as I mentioned, but I'll just discuss one of them. So that is solution combustion method. This is the one which is generally used for the synthesis of nanoparticles or nanocrystals. And sometimes this is also referred to as green synthesis, because the production of nanomaterials and products without harming the environment or human health, that is very important nowadays. Uh, so this method actually involves such principle. That is why this is also referred to as green synthesis. Solution combustion method is a very unique technique for the synthesis of the nanoparticles. It is an exothermic redox reaction between the fuel and the oxidizer. So you'll be having an oxidizer and there will be a fuel. And that fuel could be like a green material. That means it could be a gum, or it could be a tree leaf, or whatever. And what we do is, we mix this oxidizer with water and a gum or a fuel, and we'll heat it in a microwave oven, or even one can use muffle furnace. By muffle furnace, oxidation, the reaction will trigger, and that will produce nanoparticles. But this has several advantages. That is, the composition, structure, homogeneity, and stoichiometry of the products can be controlled very well by using this method. And it is very simple process, very economical and very fast process. And the exothermicity of the metal nitrate and fuel, that permits incorporation of desired quantity of impure ions. Intentionally, if you want to add some impurities, that can be done very easily through this method. And this is an example for solution combustion method. Here, in fact, this is done at our lab. So what we did was we used barium nitrate, and we mixed with appropriate quantity of water, and we used tree gum, that is eucalyptus gum, as the fuel here. And it is we prepared fuel, the gum solution, and that gum solution is mixed with this quantity, and the mixture is heated in a furnace. Then you will see that forms barium oxide. The reaction will trigger very soon. Within 2 to 3 minutes, you will see the reaction, and there will be this nitrous oxides coming out. So finally you get barium oxide. So you can see that this is the barium oxide nanoparticles. Now, if you consider the characterization of the nanoparticles, there are various methods to characterize the nanoparticles or the nanomaterials in general. We have these methods, SEM and TEM techniques, UV visible spectroscopy, X-ray techniques, FTIR techniques, and there are so many dynamic light scattering for measuring size, and so many other methods for characterization of the nanostructures. Okay, this nanostructures become, or the nanotechnology as a whole, became very much prominent because of the inventions of the electron microscopes. Before the invention of the electron microscopes, to see the smaller objects, we used to use optical microscopes. Optical microscopes have limitations. In optical microscopes, we use the visible light, whose wavelength ranges from approximately 400 nanometer to 800 nanometer. And the magnification depends on the wavelength, and we have to reduce the wavelength in order to have higher magnification. The maximum magnification that you get from the optical microscope is about 2000 times the object size. The wavelength is an important barrier for us in optical microscopes. But around 1924, Louis de Broglie gave an important theory. He said even material particles like protons, neutrons, electrons, they do have wave character. There is a wavelength associated with that. And that wavelength is at lambda is equal to h by mv, and or that is equal to h by p. Since p is related to kinetic energy, and that kinetic energy can be controlled very easily by subjecting them to a suitable potential. Hence, you can control or you can have a required velocity for the electrons, and hence the required wavelength for the electrons. That means we know how to manipulate the wavelength associated with these charged particles. That led to the discovery of electron microscopes. And for the electron microscopes, you can tune the wavelength nearly from 500 nanometer to 0.01 nanometer. In optical microscope, whatever the thing that is done by light is done by the electrons in electron microscope for imaging purpose. We'll be having, this is a simple transmission electron microscope. We'll be having an electron gun which emits electrons. We'll be having, instead of optical lenses, we'll be having magnetic condenser lenses, and we'll be having a screen, a fluorescent screen to capture the beam. But with the help of this electron microscope, we were able to see these structures very well, and that is why we have the technology now. This scanning electron microscope or transmission electron microscope or atomic force microscopes, these are used for the imaging of these nanostructures, particularly for morphological studies. For the surface studies, now we use these microscopes. In the case of atomic force microscope, there will be a cantilever with a fine tip at the edge, and as this tip moves over the surface, you will find hills and valleys, and there will be movement of this cantilever, and that movement generates a small electric pulse because it is connected to a piezo scanner, piezoelectric sensor, or you can chain a laser beam on this cantilever, and as it moves up and down, you will see that the projection of the light will be at the different places on the photodiode, and you can record the surface smoothness. That is, hills and valleys of the surface of the nanoparticles or nano structures can be recorded very easily by using AFM. Actually, this diagram very well illustrates, the things that are characterized with the help of scanning electron microscope or transmission electron microscope. Only the sample size matters. We have something called as thick specimen interaction and thin specimen interaction. And for transmission electron microscope, thin specimen interaction is observed. That means the sample size will be small. what happens is, the electron beam actually transmits through the sample to find out the inner features. It is very important. The electrons, either they go undergo elastic scattering or inelastic scattering through these electrons present in the sample, and uh, this is an important area in the transmission electron microscope. So that means we consider the electrons coming out of the sample. Whereas in the scanning electron microscope, this part is very important. So we consider either characteristic X-rays, that is well used in EDX, or OJ electrons, or secondary electrons, or backscattered electrons, or sometimes this electron may penetrate deep into the to the vicinity of the nucleus, and they produce continuous X-rays. And these continuous X-rays, this is also referred to as Bremsstrahlung. So these are some important features that are observed to show the surface features of this material sample in scanning electron microscopes. Here we have certain images taken from SEM as well as TEM. The upper row, these are the SEM images of various nanoparticles, and this is for barium oxide nanoparticles. We have some iron nanoparticles on the right side, and this is the TEM image of the nanoparticles. As we use this electron microscope for morphological information, I told you the electrons which come here. I told you here these characteristic X-rays, they are used for a specific purpose. They are used for identifying the purity of the sample. Characteristic X-rays are emitted when these incident electrons knocks off the electrons revolving around the nucleus. When these orbital electrons are knocked off from the incident electrons, so it creates a vacancy at its position, and this vacancy will be fulfilled by the next higher state electron, and that transition leads to characteristic X-rays. Since the electron arrangement is material dependent, or it is specific for a specific material, one can identify the purity of the sample by measuring the characteristic X-rays. So for that we use what is called as energy dispersive X-rays. This is a graph for a particular sample, that is BA1 nanocrystal. You can notice that this is very 100% pure. We have oxygen or only barium atoms. So if there are impurities, then also you can record the impurities. You get peaks for impurities with this same graph. To identify the purity of the sample, this plays a significant role. So this is one of the characterization tool that is used to identify the purity of the sample, that is electron dispersive X-rays. We use X-ray diffraction for two important reasons. One is to identify the arrangement of atoms or molecules in a material. I told you, all the three classes which we discussed are all in the classification of the nanoparticles could be crystalline or amorphous. Amorphous means, there will be random orientation of the atoms or molecules. To identify whether it is really amorphous or crystalline, we have to take X-ray diffraction of this sample. If you get peaks, then that confirms that, so it is a crystal, it's a nanocrystal. If there are no peaks, if this graph is smooth, then it is an amorphous substance. So by XRD, we identify whether it is amorphous or crystalline, and by using various methods like Debye method, etc., you can also find out the shape of the crystal. Suppose say it is a crystal, then you get peaks by identifying the Miller indices, HKL values. For that, one can compare with JCPDS data, and you can obtain these HKL values, and you can find out the shape of the nanocrystals that is formed. And not only that, by using this Debye method, you can find out the size of the nanocrystals. There is one more method that is called as Williamson-Hall plot. In short, we call it as WH plot. There we plot this beta cos theta. This cos theta is the off angle. Beta is now full width at off maximum. So just by plotting beta cos theta as a function of 4 sin theta, by fitting a straight line and finding the slope, it is possible to find out the size of the nanocrystal. That is called as WH plot. Hexad plays very important role in identifying whether it is a crystal, and also it helps in identifying if it is a crystal, then you can find out the size as well as the shape of the crystal. There are various softwares available now to identify these things. The other important tool that is used to characterize these nanostructures is FTIR, Fourier Transform Infrared Spectroscopy. This is basically used to identify the chemical groups present in the sample. This also helps in identifying the bending mode or stretching mode of vibrations of nanocrystals. This is for, again, barium oxide nanocrystals. You can notice that this valley represents BAO stretching mode. That is having, each chemical group will have specific wave number. So by looking into that wave number, you can identify the chemical group present in the sample. This is a very important tool to identify the chemical group in the sample. Then we have UV visible spectroscopy. I've shown again for barium oxide nanocrystals. Here, what is done is, we measure the absorbance as a function of wavelength from UV to visible reach. And in fact, here this C0, C1, C2, C3, etc., they represents the gum concentration. In fact, I told you about this. We prepared this sample by using solution combustion method, for which we used tree gum as the fuel. And by varying this gum concentration, we measure this UV visible spectroscopy for this barium oxide nanocrystals. And you notice that this peak wavelength, absorbance wavelength will be different, or this wave number will be different for different concentrations. And just by measuring this wavelength, peak wavelength, it is possible to identify the energy gap, because E is given by hc by lambda. Once if you know this lambda maximum, you can find out E, the energy gap. This is one method to identify the energy gap in the sample. But you know that the energy gap is very important property that will decide whether the material is a conductor or semiconductor or an insulator. Just to say this, you need to know about the energy gap. There are various accurate methods like Kubel-Monk method, etc., to find out the energy gap. So where you can fit the values and you can find out the exact values of the energy gap present in the sample, and with which you can identify the nature of the nano structure. Now we'll look at the applications of nanostructures, and nanotechnology has become so much important today, and we all talk about nanotechnologies because of its applications, the existing and promising applications. Okay, here there are some existing applications of nanotechnology. Mercedes-Benz that uses this application, they use paints made out of nano structures, particularly nanoparticles. The important feature of this paint is that is dirt repellent and also almost scratch proof. And in future, it could be even beautiful. The paint can change the color, and also it can self-repair if there is some scratch. Just imagine, if it is temperature dependent, so in the morning time, your car will be of some color. During the midday, when the temperature is more, it will be of some other color. And again, in the evening, the color changes. This is not very far. People are working on it. But already this scratch-proof paints and dirt-repellent paints are in the market. And this is another important application of nanotechnology that is available in the market. We have something called as antibacterial socks, odor-free socks. Uh, they are there in the market, and so these are some interesting applications of nanoscience and nanotechnology. As far as the medicine is concerned, nanotechnology is playing a very important role in the targeted drug delivery. Suppose, say, you want to deliver drug for a cancerous tissue. What we do now is in chemotherapy or some in the kind of traditional treatments, we just give medicine for the entire body. So that has a lot of side effects. But if you can target this drug only for the deceased or for the cancer cell, then you can avoid all the side effects. They're not only used in cancer treatment, for drug delivery, uh, this nanotechnology helps in a special way. We'll be having something called as nano robots, called nanobots. They carry drug to the precise point and they deliver the drug. They can, nanotechnology can be used for cell repair, etc. Nanotechnology also plays very important role in the diagnosis. So, for example, in the treatment of atherosclerosis, that is a kind of plaque that is developed in the arteries uh, due to cholesterol, can be, you know, cleared with the help of nanoparticles, which mimics body's good cholesterol, known as high density lipoprotein, that is HDL. This actually helps in shrinking of this plaque. In fact, people have experimented this and they claim that they have succeeded in the clinical trials. And very soon, this technology comes to the market. And we have nanotechnology in the cosmetic industry. Various cosmetic products are coming out with the help of this nanotechnology. In clothing, it is doing wonders to, to prepare stain-proof, waterproof, wrinkle-free textiles. We can use this nanotechnology. And some of the materials like graphenes, they have very good tensile strength. They can be used in manufacturing bulletproof jackets. And nanoscale additives in polymer composites are playing very important role in aerospace materials, because in aerospace materials, what matters is the strength to weight ratio. They should be of higher strength, but the weight should be very small. Strength to weight ratio should be very high. They use this nanofibers and they reinforce with uh, you know PVC kind of materials, and they increase the strength to weight ratio. They are used in various manufacturing of various needs, like they're used in sports items like tennis rackets, bicycles, helmets, automobile parts, etc. They're also used in space technology because the fuel is the very important criteria there. Because if you want to send a space shuttle, or say you want to place a satellite into the orbit, every kg matters. You require a lot of fuel because you have to take that entire object to the space. That is why the extraneous material, the structural materials should be of high strength but less weight. So that can be done. So we call such materials as composite materials. To prepare these composite materials, so we are using these nanostructures, and they are light in weight and they are very stiff. They are durable. That is very important. Even in civil engineering, for constructions of many civil works, we are using uh, the products made out of nanostructures. And in computers and electronic industry, this nanotechnology is already playing very important role. We know that from first generation computer to the computers that we are using nowadays, there is a huge uh, change in the processing speed. The first generation computer, in the first generation computer, we were using vacuum tubes. That is why the size was very large. But now look at the size of the mobile phones that we use. They are very fast. They can do a lot of things for us, and but the size is very small. Speed is very high. Chip, and this integrated chip will have several thousands of transistors in it, and we already reached nano size transistors. And there is an important law called as Moore's law, which says in every 18 months, the size of this IC reduces to half of its previous value. That means if the size of the chip is 1 centimeter by 1 centimeter today, after 18 months, you will see that it will reduce to 0.5 centimeter into 0.5 centimeter. Whereas the number of transistors in it doubles. This also doubles the speed. But still we are not satisfied. We are increasing the speed. You can notice here, at the beginning of this century, the typical transistor was about 150 to 250 nanometers. Look at the size. Whereas in 2014, the size came down to 14 nanometer, so that you can fill so many transistors in the same size. And in 2015, IBM has created 7 nanometer transistor. And in 2016, this Lawrence Berkeley National Lab demonstrated a 1 nanometer transistor. So that means we are already at the nano level as far as this electronics is concerned, as far as these mobiles and computers are concerned. So we are achieving greater speeds. Not only the speed aspect, even in memory devices, it could be RAM or ROM, we're using this nanotechnology. This magnetic RAM effectively save even encrypted data during a system shutdown or crash. Suppose say there is an accident. If this ROM crashes, you cannot restore the data. But this magnetic RAMs which are created with the help of this nano, they are flexible. You can bend them. So they are not affected even by crash. So such materials are developed and they are already in use. They are in market. And clean and green energy is a matter of our. You know that clean energy is very much important now, because people have already polluted the atmosphere uh, with their greediness, and we are looking for alternate resources of energy, and solar energy is one promising replacement for this. We are using solar energy. In fact, after the invention of this the silicon, germanium, etc., So there is a greater improvement in the production of the solar energy. But after the development of this nanotechnology, this has improvised even much. We have new solar panel films that incorporate nanoparticles to create lightweight, flexible, you can bend solar cells. In future, this will even it will improve, and you can paint and you can get power out of it. Not only in production of electricity, even in storage of electricity also, this nanotechnology is playing very important role. That is in the battery technology. We have developed batteries that can charge at faster rate and which can store electricity in a more efficient way, and also it can store electricity for longer time. Such things are already there in the market. And another important aspect or the application of nanotechnology is the water filter. Particularly nanofibers are playing a very important role in water filtering. You know that drinking water is very important for all of us, for the entire humankind. And the groundwater is polluted at many places, and we have a very little amount of drinking water that is available in the polar caps of the earth. And to purify this, purification of water plays significant role. That for water purification, we are using this nanotechnology nowadays. Even in agriculture sector, this nanotechnology is playing very important role. It could be in terms of prevention of certain disease for these plants, or it could be in terms of fertilizers, or it could be in terms of the chemicals that we use for various purposes. Nanotechnology is playing very important role. Here you can notice this titanium oxide doped with aluminum and silicon. They effectively control the disease in grapes, and this is the spotted disease that you find for certain grass. So that actually reduces the yield. So these can be removed. This is actually due to the development of bacteria. They can be removed or controlled. Can be controlled with the help of nanotechnology. This titanium oxide nanoparticles, they proved that they control this kind of disease in plants, and you can obtain good yield out of these agricultural things. See, environmental pollution is another major crisis that we are facing nowadays, and this nanotechnology has some solution for it. Suppose the buildings are painted with, say, the paints which are made out of this nanotechnology, particularly titanium dioxide nanoparticles, then you will see that they absorb these inorganic pollutants that are present in the atmosphere, and they can be easily washed out by the rain. In a way, by this method, you can control or you can reduce the pollutants that is present in the atmosphere to an appreciable extent. As we have so many applications with respect to nanotechnology is concerned, there are some issues, there are some potential risks due to this nanotechnology. And definitely I'll be not doing justice if I do not mention about this. One is about the health issues. People believe that, but a lot of research has to confirm this. It is not known properly. People believe that these nanoparticles, when they are inhaled or swallowed or absorbed through skin or deliberately injected, they could cause some weakening of the this immune system, or they may manipulate the functions of enzymes and proteins present in our body. That is one health issue. So we should be very careful in handling these nanoparticles. And even with respect to environment, there are certain issues. These nanoparticles, they are accumulated in soil, water, plants, etc. And if they have harmful effects, it will be very difficult to separate them out later because they are very small in size. Hence, in order to look at these issues, or in order to attend these issues, we may have to impose new regulatory methods to assess the risk management as well as to manage them. This is about nanotechnology. As we have seen, this is only a beginning. But as Payman said, there is still plenty of room at the bottom. We have a lot of things to be exposed with the help of nanotechnology and nanoscience. Nanotechnologies are really offering us great opportunities, but great power comes with great responsibilities. Only thing is we have to choose the right thing in the right way at the right time. Thanks for watching. These are some references that I've used to prepare this lecture, and almost all of them are available online, so you can just go through that for extra details. And if you have any questions, you can just raise them now.
Thank you very much, sir. The session was very informative. So we have participants all over the India. So few questions have been raised. So I will go through the questions, sir. First one is
Yeah.
from Khalil Ahmed, sir. So is same
Okay.
defects like Shocky and Frankel defects exist in nanoparticles?
Yes, they do exist. Actually, sometimes they are intentionally done by the irradiations. So because the imperfections or this crystal defects alter the crystal properties. In fact, the physical properties will change. Sometimes to manipulate these properties, they intentionally do this, and they are also present naturally, particularly in the top-down approach. So that is the major disadvantage. That is why they go for bottom-up approach to eliminate these defects in crystals. Hello.
Hello, sir. Thank you, sir. The second question is from
Yeah.
Sumalata, ma'am. So once
Yeah.
we synthesize nanoparticles and store as
Yes.
solid materials, how much
Yeah.
time it takes for function in terms of stability?
No, the stability depends. Actually, this is exactly called as aging effect. See, with age, what happens is the stability sometimes goes down, but in some materials, it will be in the opposite way. That means the stability increases with aging. So it is because of the weak bonds that is present in the nanocrystals. So people are doing experiments on this aging effects also. The stability definitely alters.
Thank you, sir. The question continues. So
Yeah.
what is the time span of the stability in
Yeah.
terms of stability purpose in chemical
Yeah.
method and green method?
Now that depends on the method. Also, it depends on the sample. In some certain samples, they study it in terms of weeks. In certain specimens, it will be studied even for years together. That depends on the sample, and also it depends on the nature of production by which nanoparticles are produced.
Thank you, sir. Now, last
Yeah.
question. So from
Yeah.
Sachin
Please.
TN, sir. So what is the
Okay.
difference between scanning electron microscope and tunneling electron microscope?
That is very simple. In scanning electron microscope, we just scan, or we take the electrons which are reflected from the sample. Whereas in transmission electron microscopes, electrons, in fact, they penetrate deep into the specimen, and in the transmitted part, the electrons are collected. Okay, so particularly to see only the surface morphology, SEM is good. If you want to see some internal structure, we use TEM.
Okay, thank you very much, sir.
Yeah.
So now it will be the end of the session. So I will
Okay.
thank Dr. T. Shivalingaswamy sir for his wonderful presentation in the topic nanoscience, nanomaterials, and their applications. And I would like to thank VVCE management and principal for giving permission to organize this FDP. And thank you very much, sir.
Thank you, Karthik. Thank you very much.
Thank you, sir.